There we go. Thank you. Um, so Stefan and I would like to present to you a study that we just completed the first stages of that we call the markers of imminent myocardial infarction. And we present this on behalf of a larger team of people, of course. Um, so, so the background for this study is that heart attacks or myocardial infarctions are still a leading cause of death globally. And we have a couple of different prevention strategies, such as population strategies, sodium taxes or tobacco taxes, or and also high risk strategies that are for healthcare to find people with a high risk of heart attacks. And since we're active in healthcare, the high risk strategy is what we're most keen on evaluating, because that's our job in healthcare to carry out. And Jonathan Emerson has shown in this article that I referenced 20 years ago that the high-risk strategy is clearly insufficient to find people at high risk for a heart attack to a sufficient extent. There might be a couple of problems with the current high-risk strategy. Specifically, we use risk scores like the SCORE2 algorithm that have a 5 or 10-year horizons, and they rely on stable risk factors, of course, because they need to sort of have a stable prediction over 10 years of time. But we also know that motivation by the target populations for long-term preventive drug treatment is really limited. If you start people on a statin or a blood pressure lowering drug, or aspirin for that matter, we know that only 4 out of 5 will at some point during follow-up be taking that drug. And if you ask people if they've taken it since they started on the drug, that's just about 50% after a couple of years. So it seems like people are not super keen on taking their preventive drug treatment. We also know that the months before a heart attack are really dynamic. So a couple of these references show that if you are bereaved your significant other, your partner, your risk for a heart attack is doubled in the months after that bereavement. And also, if you get a cancer diagnosis, this is the New England Journal of Medicine reference in the middle there, the risk of a cardiovascular death is increased 5-fold in the week after that cancer diagnosis, and is doubled in the following month. And that has nothing to do with the actual cancer, but it has to do with the stress of getting this diagnosis, because most of these cancers were sort of slow growing. So, and also one of those references say that it looks like if you look inside the coronary arteries of people with a heart attack and look back at previous angiograms in the months before that heart attack, it seems like plaques in the coronaries that were previously stable change a lot in the month before a heart attack. And we just don't have a lot of data on what happens in the blood and in the coronary arteries in the months before a heart attack. So our hypothesis was that several distinct dynamic biological processes are likely to be active in the months before a heart attack. And we think that it would be possible to find biomarkers of these processes in peripheral blood in the months before a heart attack. And we also think, on a side note, that these heart attacks should be able to predict using simple prediction algorithms that we could develop. And we also hypothesize that showing people that their risk of a heart attack in the following 6 months might actually motivate them better for long-term preventive drug treatment. That's for other trials to figure out, and we're actually designing that trial as we speak. But for the purpose of this metabolomics or proteomics talk, let's focus on the biological understanding of what leads up to a heart attack. So with this hypothesis and this rationale for a study, we approached cohort studies throughout Europe, and we were fortunate enough to have a call that specifically met our needs from the BBMRI LPC project. The BBMRI, you know about, that's the biobank, again, molecular resource infrastructure throughout Europe. And the LPC, that stands for Large Prospective Cohorts. And you could participate in that project if you were a cohort that had a biobank and were willing to share blood with researchers. So this was an effort to increase biobank usage. So they had an open call, and we were fortunate enough to place at the top of that call. So we had the biobank extractions funded through this through that project. So we're very grateful for that. And these are the cohorts that participated in blue, and we'd like to outstretch our thanks to those as well. Of course, we programmed the inclusion criteria for this trial, and that was that you had to be free from for this study. You had to be free from all kinds of cardiovascular disease, and you had to have biomaterial in freezers that you were willing to share. And we ended up with 169,000 people who fulfilled those criteria, who were heart healthy, so to speak. And then we, out of those 169,000, we selected cases of a first myocardial infarction within 6 months after the blood draw. And that happened in 420 people. So that's a fairly unusual event, of course. And then we constructed a stratified case cohort study. So in these cases, we defined the median age and the sex of people, and then we went back to the cohorts and asked for a subcohort that would represent the original cohort, and that cohort was then stratified and based on the age and sex of the cases for an efficient study design. So we ended up with 420 cases and a subcohort of 1,598 people. And coincidentally, and none of the people in the subcohort and the cases overlapped, which they, of course, could in a case cohort design. And then we asked for the blood, and it came to us in these wonderful shapes and forms. I specifically like the straw from the Estonian biobank. I think it's kind of neat. And then we went to our statisticians to have help randomizing these samples onto plates. And of course, this had to be done in a couple of steps, keeping the blood cold while randomizing them into these boxes, and then aliquoting those onto the plates, because some of the analyses have pretty significant plate effects that Stefan might talk about later. This is Gitta Högberg, who's our wonderful assistant who did all of this work. This is what the freezer ended up looking like. And we've spent the proteomics and metabolomics plates, but we still have plates biobanked for all of these participants to the right here. We of course needed a number of clinical variables to understand the data, and we had a pretty long process, a couple of years of process of getting access to these clinical variables and harmonizing them in a manner that was representative of the data in the cohorts, with a long dialogue, of course, with the participating cohorts. And I think I'll hand over to Stefan now for descriptions of the QC steps that we did with all the blood.
Yeah, so I will go through some of the methods and results before the break. And to start with, these are the numbers that went into the analysis. First of all, we excluded samples that failed for technical reasons or where the sample volume was deemed too low, around 1% of the total material. For the metabolites and proteins, we required that they were measurable in at least one patient in each cohort and that they were present in at least 30 individuals in total in the entire material. And with those filters applied, we ended up with around 1,000 metabolites, 800 proteins, and around 16 clinical covariates. And with clinical covariates, I mean variables such as systolic blood pressure, BMI, smoking status, and a few others. And these were measured in around 400 cases of imminent myocardial infarction and around 1,600 non-cases. Sorry. Now, before running the actual analysis, we performed several quality control checks. I will just mention a few of them on 2 slides here. First of all, we looked at the correlation between clinical covariates measured on the Metabolome platform versus the same analyzed measured using standard targeted methodology. And for example, in these 2 scatter plots to the left, we look at the correlation between total cholesterol and glucose measured using the Metabolome platform, and these standardized methods which are targeted. And overall, we found a very good correlation that was consistent across cohorts. We also compared metabolite levels versus questionnaire data. For example, we look at self-reported smoking status versus nicotine metabolites in the patient's blood. And again, found a very high correlation. For example, current smokers, those were the ones that had high levels of these nicotine metabolites, whereas never and former smokers had values close to zero, with a few outliers, potentially representing incorrect answers to the questions or for patients that used other nicotine products. Now we also looked at expected association with clinical covariates. And then, for example, we saw that the strongest correlates with sex. Those were androgen and estroid steroid hormone metabolites, as expected, which almost separated perfectly with sex. And on the proteomic side, we saw that leptin and fatty acid binding protein 4 was the strongest correlate with BMI, which is also expected and has been shown in previous studies using the Olink data. And all of these estimates were also consistent across cohorts. So based on these quality control checks, as well as several other checks, we concluded that our data was in pretty good shape for analysis. Now, in the data, there are several sources of missingness. The measurements can be below the lower limit of detection, they can have failed for technical reasons, or they can be truly absent in the sample. And the missingness also varies greatly between the metabolite categories, for example. If we look in the figure to the upper right, we see the proportion of missingness on the y-axis versus different metabolite categories. And it might be hard to see the labels here, but for example, the rightmost category, that is xenobiotics, which has a very high proportion of missingness, probably due to these xenobiotic metabolites being absent in the samples. The way we handled these missingness varied between the proteomics data and the metabolomics data. So for the proteomics data, we used the actual machine values below LOD that we actually got. And here it should be mentioned that the LOD cutoff from the Olink platform is actually very conservatively defined. It's the maximum LOD across all plates. So if you have an experiment with many plates, you will get a quite conservative LOD cutoff. And without going into too much detail about that, we have seen that in other projects as well, that you can for sure get useful information below this LOD cutoff. Of course, the measurement error increases continuously the further you go below this cutoff, but it's certainly not random noise below this cutoff. On the metabolomics side, we use a constant value replacement for the values below the minimum, together or without the missing indicator method. And that is a really simple method referenced here, where you, in addition to this constant value replace variable, add a 0,1 dummy indicator for whether or not the value was below the minimum or not. And that method has shown to perform very well when it comes to bias in the parameter estimate, even in the presence of a high proportion of missingness under some other scenarios in previous simulation work. We also ran our own basic simulation, so to set up for our own type of analysis, and came to a very similar conclusion that this simple method performs very well with regard to bias in the parameter estimate, even in the presence of quite high proportions of missingness. Now then, we have the clinical covariates and a few other technical failures that contributed with missing values, and those were imputed using multiple imputation with chained equations. Now, we always adjusted our models for technical covariates, and those were storage time, cohort, batch, or plate. So the sampling collection period for the MIMI study is quite broad. It ranges from the very first sample collected in the EPISC study up to the very last sample collected in the EpiHealth study, and that spans more than 24 years. We ran a principal components analysis for the protein metabolite matrix, and there we saw that the first principal component, explaining most of the variance in the data, was highly correlated with cohort, and in particular the epi cohort. And the top loadings of that first principal component was citrate and EDTA, indicating that sampling handling and the anticoagulant used in the blood samples differed between cohorts, which was the main driver to this difference in variation, in addition to large differences in storage time as well. Then we also considered batch and plate, and both the Olink and Metabolon data comes with normalized values as default. And that has at least before been a median centering of the values across plates. So if you have unnormalized data, as in the example to the right here, you center everything at the same median. And this, of course, then assumes that you have random placement, which we have in the MIMI study. The samples have been randomized to the plates, and we have about an equal proportion of cases and non-cases on each plate. Then in addition to these technical covariates, we then added on an adjustment for age and sex, and then additional adjustment for confounders, systolic blood pressure, BMI, and creatinine as a proxy for kidney function, in an attempt to get the total effect estimate, including the effect of mediators. Now, as Johan mentioned, our sub-cohort representatives, they were randomly drawn 1 to 4 to each case of imminent myocardial infarction. Now, would we use our material as is in, for example, an unweighted Kaplan-Meier analysis, that would give us an estimate of a 20% risk of developing myocardial infarction within these first 180 days or 6 months. But that risk estimate is representative of the sampling design and sort of the data we have available to us. The estimate we're really interested in is the estimate of the total cohorts from which our sub-cohort was drawn. So our sub-cohort participants, they need to be upweighted so that they represent the large pool of participants in the full cohort that they represent. And if we apply this weighting, we will get a reasonable risk of far less than 1% of developing myocardial infarction within the first 6 months. However, these sampling weights, which are based on the inverse variance of being drawn, the probability of being drawn, those sampling weights are not supported in all statistical functions. So that could be something to be aware of. And that sometimes causes issues when you want to apply a certain method and then it doesn't support these sampling weights. And in addition to the sampling weights, we also calculated robust standard errors, which is typically done in this case cohort design. And with that, I will end for the break and continue after that.
All right.
Thanks, Stefan. Over to you, Natasha.
Yes, thank you so much. That was very interesting and always very nice to see the amount of work that actually goes into getting the data into shape for statistical models. It's not something that we see very often. So thank you very much for making that part of your presentation. So we're very excited to hear more from you shortly about the results and the prediction, the process of developing the prediction model. In the meantime, I'd like to take the next few minutes to provide a quick overview of Metabolon's technology and how metabolomics can be readily applied to enhance population health research such as yours. So let me just share my screen. All right. So understanding and effectively treating complex diseases such as cardiovascular diseases and myocardial infarction, as presented by our speakers today, is of course a very challenging topic, mainly due to the interplay between the many factors that influence these phenotypes. And we know that large-scale cohort studies have become indispensable in unraveling these complexities, as they provide us with invaluable data that helps us understand how genetic predispositions, environmental exposures, as well as different lifestyle factors all interact between themselves to influence disease development and progression. And we're all witnessing how metabolomics is becoming increasingly popular in population health studies, as well as the wealth of insights that we have gained to date from studies like this. One very important observation from many of the studies is the pleiotropy that metabolites exhibit, meaning that a single metabolite can influence various different pathways, impacting multiple physiological processes and disease states. And this is where multi-omics data integration becomes a very powerful tool, as we have and will see more from Johan and Stefan. So when multi-omics data integration is performed correctly, it can provide us with a more comprehensive view of biological systems and the interactions between the different omics layers and the different molecular levels. So naturally, once findings from the studies are validated, this information can be used to develop new disease management strategies, including disease prediction tools, which is, of course, the topic of today's webinar. At Metabolon, in our untargeted metabolomics platform, has been widely used in some of the largest and most important population health studies across the world. There's been a tremendous amount of data and knowledge that has been generated through this discovery work. And we're actively and continuously working towards partnering with different organizations, profiling large cohorts of individuals from the general population or from disease-specific cohorts, always aiming to address questions that are related to different disease mechanisms or processes like aging, environmental exposures, dietary patterns, with, of course, the ultimate aim to be to contribute to the improvement of the health status of these populations. So over 1 million samples have actually been run on our untargeted metabolomics platform today. And the platform has become a widely used tool for biomarker discovery studies due to several key reasons. Firstly, is our metabolite coverage. The discovery methods that we use are all LC-MS-based and have been designed for maximum metabolite coverage. Given the complexity of biological matrices that are typically collected in population health studies, such as plasma and urine, we use multiple and complementary LC-MS methods, running each sample that comes through our lab using 4 different analytical methods in order to maximize metabolite and lipid coverage. Second, we're able to deliver level 1 metabolite annotations, leveraging our library of close to 5,500 authentic chemical standards. And everybody in the metabolomic space can absolutely appreciate the bottleneck that is accurate metabolite identification. At Metabolon, we follow what we call a chemocentric approach, meaning that metabolites are identified prior to statistical analysis, as opposed to the ion-centric approach that tries to identify ion features after statistical analysis. So from the 150,000 features that are generated from our experiments, we identify metabolites using their retention time, their mass-to-charge ratio, and their fragmentation pattern. We then confirm those identifications by matching them to the same signatures that we have obtained through our library of standards. So these standards have been run on our platform, so we know exactly how they behave in our analytical environment. So this reduces false discoveries and removes noise and redundant signals from these data sets, leaving only biologically relevant metabolite signals that can be used for subsequent statistical analysis and evaluation. And finally, our global metabolomics service includes by default access to our bioinformatics platform. So we don't stop at just data generation. We have our bioinformatics platform that offers very powerful data analysis and visualization tools. We're going to go through some more details in just a couple of slides, but I highly recommend that you visit our website to explore and demo these features. And additional to that, we provide expert support and consultation prior to sample analysis. So we guide our investigators throughout the study design process. And we also actively participate in the biological interpretation of the data to ensure that investigators extract as much value as possible from their data. So we help interpret these complex signals that come from these rich data sets, identify and help you identify and communicate the findings of the study, and provide guidance towards what the best next steps would be. Here we're looking at the expected metabolite detection capabilities of our global discovery panel across various biological matrices. For instance, just looking at plasma, we can detect and confidently identify an average of 1,200 metabolites, with 80% of them being level 1 annotation. So their structure is confirmed using authentic chemical standards. But we also report on known and known metabolites, so compounds that are frequently detected but are not yet fully characterized. But it's data that can absolutely be used in statistical analysis. With that said, each reported metabolite is mapped to a primary pathway and different subpathways, providing very important insights into the function as well as the biology of each metabolite. And we currently cover over 70 such metabolic pathways, including key groups like amino acids, lipids, xenobiotics, drug metabolites, and of course, microbiome-associated metabolites. The final data set is delivered in a plug-and-play almost format, so the data is processed and quality-checked, annotated for immediate use in statistical analysis and biological investigation, eliminating the need for complex data processing. And in line with that, our objective was, of course, not only to generate high-quality data, but to also generate insights and knowledge. So early in 2024, we launched our integrated bioinformatics platform, which addresses some key challenges that are faced by investigators in metabolomics data analysis. The platform simplifies the analysis process and it accelerates insights generation, and it, of course, reduces costs and resources associated with the analysis itself. It integrates global discovery metabolomics data with user-friendly and very interactive tools that have been designed to guide the users in understanding the biology behind the data. The platform integrates several tools, including traditional univariate statistical methods, as well as different multivariate data visualization methods, such as principal components analysis, PLSDA, and the users also have the option to perform pathway analysis and also use our biomarker lenses, which offer biological insights behind every metabolite in the data set through the lens of a disease or a specific metabolic pathway. And finally, for added transparency and for users who want to do even more with their data, we're excited to offer access to raw spectral data, allowing our users to process the data in their preferred workflows and to also search for metabolites that might not exist in our library. So this feature is ideal for researchers and advanced users who can apply their own data mining techniques to discover hidden patterns or metabolites, and also investigators who want to deposit the data into repositories that can be made publicly available to the community. So that's all I wanted to share with you today regarding our technology and solutions. So with that, I will pass the baton back onto Stefan for the second part of today's webinar, where he will be discussing some of the group's work on biomarker discovery methods and present some of their results too.
Right, so the main analysis that we performed, those were Cox proportional hazards regression model, where we tested each biomarker one by one in separate regression models versus the 6 months risk of myocardial infarction, adjusting for these covariates that we mentioned on the previous slide. This figure to the right is a volcano plot showing the significance on the y-axis, the minus log 10 p-value, and the effect size, the log hazard ratio on the x-axis for the different metabolites, proteins, and clinical covariates included in our tests. And it's the top 25 findings that are highlighted in this specific figure. Now, in addition to these one-by-one regression models, we also performed a joint modeling of all biomarkers together in the same model. And here we tried a few different strategies, lasso regression, for example, and decision tree-based method. However, those methods did not really reveal any major additional finding on top of what we found in the one-by-one regression models. potentially due to power issues, which we will come back to, because some of these methods are quite power hungry. Now, our main approach for validation, determined a priori of running the analysis, was that we would run a discovery analysis in 3 of the cohorts, making up around 70% of the material. And then we would validate the results in another 3 cohorts of the mini study, the remaining 30%, which was completely set aside for this purpose. So this is something that could be considered as an external validation because it's a completely new material, so with completely new cohorts that went into the validation. And results with a false discovery rate less than 0.05 in the discovery and with the same direction of effect in replication together with a p-value less than 0.05 in the replication were considered validated. This is a forest plot again of the top 25 results where we have the discovery point estimates in blue together with a 95% confidence interval and the validation point estimate in orange or red. Now here it should be mentioned that we had this power issue. So several of our top findings, they passed an FDR less than 0.05 in the full MIMI material, but did not survive this validation approach for most of the cases, potentially due to power issues, because originally we had planned to include more centers, but then it turned out that some of these centers could unfortunately not be used to legal issues that had arisen. So a sample size was unfortunately a bit lower than what we would have planned for. So we for sure had some power issues in this analysis. Now our most robust and strong finding was brain natriuretic peptide, a protein, which previously had been mostly associated with or used in diagnosis of heart failure. It's a marker of ischemia and a marker of damaged cardiomyocytes. And this finding was consistent or mostly consistent across cohort. We found both a strong association with the BMP form as well as the NT-proBNP form. And it was mainly the very high levels of BMP, the 4th quartile, which were associated with the highest risk of imminent myocardial infarction. Now we also looked at if there was a time interaction with the biomarkers with regard to the effect of imminent myocardial infarction. So let's say that it's a certain metabolite associated with the risk of the first 3 months versus the last 3 months of this 6-month period of evaluation. But there we didn't really find a strong interaction with time in the analysis that we ran. We also compared the 6-month risk of myocardial infarction as estimated in the MIMI study versus the long-term risk of myocardial infarction over 10 years as estimated in a completely different cohort, the PIVU study, which is a cohort study from Sweden of elderly individuals of around 70 years of age. And this figure shows on the y-axis the effect estimate from the MIMI study, that is the short-term risk of MI, and then on the x-axis we have the long-term risk of MI from the PIVU study, both in Cox proportional hazards regression model. Although this isn't a formal test, we can see somewhat of a trend that among the strongest results that are associated with the long-term risk of MI, many of those have the same direction of effect when it comes to the short-term risk of MI. Some of the findings, they are found to pass FDR less than 0.05 in both these analyses, for example, KIM1 and GDF15, whereas other results have a stronger association with imminent myocardial infarction rather than the long-term risk of MI, for example, brain natriuretic peptide, which I mentioned on the previous slide. And I think I will actually hand over to Johan here for summary of the results and description of the prediction.
And I think you can go through that slide as well, Stefan. I'll talk about the prediction model after that.
So in summary, we found several biomarkers involved with pathways with a clear link to CVD, such as inflammation, extracellular matrix modeling, hypertrophy, apoptosis, and cell adhesion. In addition to that, we found several biomarkers with an unknown etiology, for example, this vitamin C derivative. It should be mentioned here that many of the metabolites actually had a quite unknown connection to myocardial infarction, potentially representing novel pathways. We found several biomarkers that had previously been associated with CVD, such as IL-6. Several of them are probably markers of ongoing ischemia rather than being causes of myocardial infarction, for example, brain-attenuated peptide. Some of the metabolites, they were of unknown identity at time of publishing our paper. They have, however, with the help of metabolome later been identified. For example, this unknown X metabolite here. Here we at least have gotten the possible class of the metabolite, which is a nucleoside derivative. And interestingly, that specific originally unknown metabolite has also been associated with a closely related cardiovascular phenotype in a totally different cohort study. That is still not published, so I can't really go into details there. But that could be good to know that even after the study has been performed, it is possible to, for some metabolites, get the identity of them even for the unknowns.
Great, thanks, Stefan. Just to clarify, NT-proBNP, then, I mean, it's a marker of myocardial strain, and one of the first things that happen when you have a coronary occlusion or narrowing is that you get ischemia in the myocardium, like Stefan said, and that per se leads to a diastolic dysfunction, and that's what we think causes the strain that gives rise to this NT-proBNP. So it's not a sort of classic marker of ischemia, but the ischemia does lead to diastolic dysfunction. Okay, so we used the same setup that Stefan told you about with the weighted Cox proportional hazards model, and we introduced a ridge strategy in here and derived a prediction model for developing a first myocardial infarction within 6 months. And well, you can see the nomogram here that goes with the model that's in the paper. I think you can find the paper in the resources to the right of this presentation. There are some tools that come with this presentation. So you have a link to the paper and to the prediction model. But this is sort of easy finger counting. You could just, using a person's age, you could gather points, and then you move down to their sex, and you gather points for that, and then diabetes, education, etc. And you just work your way down this nomogram. This prediction model achieved a pretty good discriminative performance in the validation sample of 0.78. And we compared it to the SCORE2 model. That's the one used currently in clinical practice that predicts outcomes on a 10-year horizon. But it's of course possible to adapt that to a 6-month horizon, and you can see that. And actually, the discrimination was about the same of the SCORE2 model in this sample, but it severely overestimated risk. So the calibration was poor for the SCORE2 model. So we took this to an independent sample, the UK Biobank, and did the same. We used these same algorithms, the original one, MIMI one, and SCORE2 one. But then, as you should do for all your prediction models, we also transposed it to the UK Biobank sample that has a much lower risk than the original MIMI sample had. Some of the feedback we got when we tried to get this work funded was that it's going to be impossible for you to get blood from so different cohorts, and the predictor models are not going to work because you're having data from cohorts with so different base hazards. But I actually think that the opposite is true, that the more cohorts that you have, the more externally valid your prediction model will be, because it doesn't sort of overfit to one single cohort profile, but rather gets sort of dumbed down to fit most cohorts. That's the reason why we do multi-site and multi-country clinical trials as well, multi-center trials. Okay, so decent performance of this clinical prediction model. The counting of points here might be cumbersome. So Stefan also, I should say that the previous model that was in the paper was done mostly by our colleague Erik Lampa in our group, but Stefan has also translated this into a web-based format that you can find using this link, miscore.org. It sometimes doesn't work for me in Safari, but it works better on Firefox and Chrome. And here you can sort of use sliders and drop down menus to enter your personal values or the values of your patient into the algorithm. And then you get the whole equation here, highlighting the person's mean values in bold, and then you get the prediction. Of course, getting a first heart attack within 6 months is really unusual. So most of the time it's going to say less than 1%. We also didn't want to point out risks that are super high, such as 50% plus. What you can do is you can work with the advanced settings here, and I think Stefan introduced a lovely little warning saying that this is really just for advanced users, so don't attempt to do this on your own. But you could change from the mean values, because that's I don't know if you're familiar with this this way of calculating risk using the Cox model, but you need to sort of subtract the mean values of your population from the values of your patient in front of you. So you could change those mean values to other cohorts, such as the UK Biobank, for example. But you can also enter your own values for your own population, your own risk set. And that's really, of course, for advanced users, but could be useful for you if you want to apply this to your own cohort, for example. Do you want to say anything else about this, Stefan? Or was that a fair description of what you did?
Yeah, no, I think that's a good summary. We're also considering adding a new version of the calculator where we, in addition to the absolute risk, also provide the relative risk for a reference individual with the same age and sex and with sort of optimal values of these covariates, because the absolute risk will, of course, often be very low.
Yeah, great. And we're exploring that with communication experts and patient advocates as well, and try to see what's the best way of communicating this. Great. So just to sum up, we identified 94 biomarkers associated with the risk of an imminent first myocardial infarction. I mean, we could say novel, because to be fair, no one's ever tried to predict a first myocardial infarction within 6 months. So everything's novel here. BNP was the most consistently associated with an imminent myocardial infarction, but it didn't really improve our prediction models. So we developed and validated the first prediction model, had the fair ability to discriminate between cases and non-cases within the next 6 months. I think personally, and that was part of our hypothesis, that this might enhance the motivation of patients and doctors for primary prevention. Hearing that your risk is your absolute risk is a certain number over 10 years maybe doesn't motivate you as much as hearing that your risk is twice as high as it could be for a heart attack within the next 6 months, for example. We did have substantial power issues, and this is, of course, both a blessing and the curse of multi-omics projects. And here in this project, we had 1,800 biomarkers. So we're now looking at ways of diving deeper into sections of this vast database, and we're very open for collaborations if you think these data are interesting. This is the paper. There's a link in the sort of show notes to the right, and these are email addresses if you want to discuss anything with us. Stefan, of course, for methodological questions, and myself for the more clinical ones. Thank you.